remember that we talked about two different ways that you can handle gas law problems, or two different ways that you'll see gas law problems presented. One of which was we have the equation PV equals nRT. We're going to have or be able to calculate 4 out of the 5 of those particular values, and we will have to use algebra to determine the other one. I call that the plug and chug method. Second method is what we call the initial final calculation, and it relies on the fact the gas constant will remain constant, which is why we call it the gas constant, at any set of conditions. And that's a pretty good assumption. It works under most situations that we are going to see gases under, or we're going to, at which we'll be studying gases. And so we are going to then be able to rearrange the ideal gas law into one side of an equal sign, one expression for an initial set of conditions, and another expression for a final set of conditions. We've got the initial pressure times the initial volume over the initial number of moles times the initial temperature. And that's going to be equal to the final pressure times the final volume over the final number of moles and the final temperature. And if you look at that, each side of this equation is actually the gas law that's been solved for R. So this equals R, so if we put all those values in for an ideal gas, we calculate it should come out to be the value of R. This set of conditions, which are the final set of conditions, if we would plug those into the equation, that value for the pressure times the volume over the number of moles times the temperature should equal the gas constant. So what we're doing is we're relying on the fact that that's a constant, and we are able to make an expression for initial and final set of conditions. In this case, the way that I normally do the problem is I will write out my set of initial conditions and my set of final conditions, one on each side. So I write the expression like this, and I'll put the values on each side of that particular equation. So what I mean is I'm going to have an initial pressure, an initial volume, an initial number of moles, an initial temperature. Okay? Then I'm also going to have a final pressure, a final volume, a final number of moles, and a final temperature. In this problem, it says that we're taking helium. It's in this gas cylinder. Remember, gas cylinder very high pressures, so that we can squeeze it down, take out some of that free space, and we can store a large amount of gas in a very small place. So we can take it and use it in the laboratory, for instance, and it's not going to run out right away. It will last for a long time. So that gas cylinder has a volume of 29.5 liters, okay, at 300 atmospheres. 300 atmosphere. So we know the initial volume is 29.5 liter. And we know that that initial pressure of that gas is at 300.0 atmosphere. Now we're going to take that gas, we're going to let it out into a room where the pressure is 1 atmosphere. So that final pressure is going to be 1.0 atmosphere. We want to know what volume will that gas occupy at that particular pressure relative to the 300 atmosphere that we had initially. Now, one thing you're going to notice about these types of problems, there are lots of variables here. And you might be sitting there thinking, I've got to know all of them, and in this problem they've only given me 3. One of the things that you're going to have to realize is that whenever they don't tell you anything about the number of moles, or they don't tell you anything about the temperature, that means that it is not changing. So you can make the assumption that those things are not changing. So the moles initial and the moles final are going to be equal. So they will cross out of the expression. Same thing. If the temperature initial and the temperature final, they don't tell us anything about those temperatures, then we assume the temperature is the same under both sets of conditions, and the temperature would cross out, which now leaves us with this simplified expression: pressure initial times volume initial equals pressure final times volume final. 4 different variables. We have 1, 2, 3 values. We can calculate the 4th. At this point, it just becomes plug and chug. Now, there are going to be some things about this. With this initial final pressure type calculation, it's going to be very similar to the dilution equation, where we said, in the dilution equation, we don't always have to use liters, even though our concentration, our molarity, is in moles per liter, because they're going to cross out on both sides. In this case, volume units won't really matter because they're going to cross out. And pressure units won't really matter because they're going to cross out. They're going to be, as long as you have, if you would have torr on this side, you would have to have torr on that side. Now that said, I almost always, when I'm dealing with the gas law, would calculate everything in terms of the units that I would normally for the gas law. Get into that habit. The other thing to mention is, the one unit that it absolutely is imperative that you always use the correct one or the appropriate one is temperature. A lot of times students will say, okay, well, the temperature is here on both sides. As long as I use the unit here and it's the same, it won't matter. In reality, it does. Okay? Temperature has to be in Kelvin. Can't be in Celsius or Fahrenheit. And the reason for that is that the conversion factor, or the conversion of temperature between Kelvin and Celsius, requires an addition step. All right? So it makes it not so simple to just use Celsius here. You always have to use Kelvin in any type of a gas law problem. So now we've got this equation, we can just start plugging things in. 300 atmosphere, 29.5 liter, 1.0 atmosphere, and we have some final volume. So literally it is just some basic algebra at this point. You solve for it. We should end up with 2 significant figures because this 1.0 has 2, and we've got 3 and 4, so it's going to be the smallest because it's all multiplication and division. And so you should end up with that final volume equaling 8,900 liters. Okay, now, does the answer make sense? Well, we've got a little bit of gas stored at very high pressure. Remember, the high pressure will push the molecules or the atoms that are in that gas together. It takes away some of the free space. So then when you let it out into an environment where the pressure is lower, then all of a sudden that gas will expand again. We're letting up on the pressure, so the gas expands. The volume should go up significantly. And indeed, it goes from about 30 liters to about 9,000 liters. So it significantly expands, which is exactly what we would expect based on what we know about gases. So this answer, does it make any sense? Yes, it does make sense. There are those clues again that we can use to try to figure out, does our answer make any sense whatsoever? One of those things I've sort of been harping on you to think about the answer that you're calculating instead of just trying to calculate a number. Initial final gas law problem.